Before I continue my explanation on the principal operation of single-phase uncontrolled rectifiers, I would like to share my tips to sketch a bridge rectifier quickly. If you look on the circuit topology of the rectifier, you can see that the circuit consists of two frames. By imagining the window of the classroom, you can start your sketch by drawing a large square window. Next, split the window into two frames. On the left frame, you need to add 4 diodes, 2 at the top and another 2 at the bottom. Then we label all the diodes according to their pairing. I will explain later about the pairing when we discuss about the principal operation of the bridge rectifier. Next, you need to focus on these connection points, where based on these 2 points, you can see that actually this AC source is connected at the middle of the frames. So you can add the AC source here. Once again, don't forget the label. Show the polarity for the supply voltage. And based on the positive polarity, you label the supply current. Here you can see that actually the AC source acts as the bridge between the first and the second legs of the rectifier circuit. Lastly, on the third leg, you need to add the DC load. You can add the resistive load, a resistive load, or an inductive load. You need to label the output current first. And based on the output current direction, you can determine the polarity of the output voltage. For future analysis, I prefer to use this circuit topology instead of this circuit topology. Now, I will explain the last topic for this video, which is the principal operation of single-phase, uncontrolled, half-wave and full-wave rectifiers. As mentioned before, a rectifier converts AC power to DC power by controlling the current flow using power switches. In the context of the uncontrolled rectifiers, we need to focus on the operating conditions of the diodes. However, we must assume all the diodes are ideal. Figure 4 shows voltage and current waveforms of an ideal diode. Based on the figure, we can see that the diode can work in 2 operating conditions, forward bias and reverse bias. These 2 operating conditions depends on the current flow towards the diode. If current flow to the anode terminal, the diode is in forward bias. In this condition, the diode will act as a short circuit to conduct a very large current from the source to the load with zero voltage drop. Nevertheless, when current flow to the cathode terminal, the diode is in reverse bias. In this situation, the diode will act as an open circuit to stop current flow by blocking a large reverse voltage. As a result, we can see in figure 4 that we only have a current waveform during forward bias and voltage waveform during reverse bias of the diode. As the direction of current flow depends on the polarity of a voltage source, it's better to explain the principal operation of the rectifiers based on the waveform of a single-phase AC supply voltage. During the positive half cycle, diode D in the half-wave rectifier is in forward bias. Hence, it creates a closed-loop circuit to conduct current from the source to the load. Meanwhile, in the bridge rectifier, diode D1 and D2 are in forward bias. Thus, current can flow from the source to the load. Here we can see the bridge rectifier requires a pair of diodes to conduct the current. On the other hand, in the split supply rectifier, only diode D1 is in forward bias. Hence, current will flow from the source to the load. Next, when the half cycle of the AC supply voltage waveform is negative, diode D in the half-wave rectifier is in reverse bias. As a result, it creates an open-loop circuit and therefore current cannot flow to the load anymore. Nevertheless, in the full-wave rectifiers, current is still flowing to the load. It is because in the bridge rectifier, diode D3 and D4 are in forward bias, while in the split supply rectifier, diode D2 is in forward bias. That's all for today, and I will see you again in the next video.